and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Josh Kramlick.
Hello, everyone. Thanks for joining us today for this week's session of Tech to Tech by KYZEN Corporation. My name's Josh Kramlick. I'm the Americas manager here at KYZEN. And today we're going to be talking about ultrasonic frequency selection in parts cleaning. I've been fortunate to work with a number of ultrasonic technology companies over my career, so I've had the benefit of a lot of practical experience in this exact application. So first, some basics. Let's talk about sound versus ultrasound. I think most folks generally understand this, but human hearing, typically in the range of 20 hertz to 20,000 hertz or 20 kilohertz, and ultrasound is typically considered anything above this audible range. In practice, however, ultrasonic cleaning applications can actually be as low as 15 kilohertz, especially those utilizing older magnetostrictive technology as opposed to piezoelectric technology. So next important thing to talk about is sound propagation. So sound waves can propagate through almost any media with varying degrees of efficiency, the exception, of course, being vacuum. In sound wave propagation, we have these regions of compression and rarefaction. Compression are the high pressure regions in the sound wave, and rarefaction are those low pressure regions. It's in these low pressure regions that we create the magic of cavitation. And here in the sequence of photos, you can see the collapse of a cavitation void ending with that very stereotypical microjet burst at the end, which creates the cleaning activity. So there are two defining characteristics of sound waves, frequency and amplitude. Frequency, of course, is the number of compression rarefaction cycles per unit time. This is typically expressed in hertz. It's often thought of in audible sound range as the tone of a sound. And just as a note, doubling the frequency simply would mean doubling the number of cycles per unit time. Increasing frequency reduces the time that cavitation voids actually have to grow before they can collapse or implode on themselves. This higher frequency results in a smaller cavitation void, and those smaller voids implode with less energy than larger voids. In contrast to that, lower frequency ultrasonics obviously create larger cavitation voids, imploding with greater energy. And here in the animation on the left, we'll see the very left side is a lower frequency and the right side is a higher frequency. And what you'll see is that each cycle, the lower frequency has a larger cavitation event than the cavitation event in the high frequency animation. Next, we want to talk about amplitude. The amplitude of a sound defines the intensity of the compression rarefaction cycles. This is commonly thought of as loudness for audible sound. Higher amplitude means higher pressures, and that would be equivalent to the higher decibel level in audible sound. Decibel level, of course, being a logarithmic measure of sound pressure. So we have another similar animation here. On the left, we have left and right are the same frequency. The left has a lower amplitude than the right. As we increase this amplitude, we increase the ultrasonic power. That additional ultrasonic power induces more cavitation events within the bath. Those greater number of cavitation events equate to a higher cleaning activity in the bath, but the size of the cavitation voids remains really constrained in general by the frequency that you're operating at. So what you'll see here on the left, again, both same frequency, but we're showing that with the higher amplitude on the right, we're getting a higher number of cavitation events per cycle. So what does it all mean in parts cleaning? What we'd like to show you here is sort of the whole range of industrial cleaning applications, from gross cleaning, what we would say is over 400 microns, up to the Megasonic cleaning for semiconductors. In gross cleaning applications, such as maybe carbon deposits, sand castings, forgings, really in a lot of cases, those parts can be cleaned very easily with just spray applications because the particles are large enough that separating them from the surface doesn't require the intense energy of ultrasonics. As we move into more general industrial cleaning applications such as machine parts, hardware, automotive applications, we'll commonly see frequencies in the range of 25 kilohertz to 60 kilohertz employed there. 40 kilohertz is probably the most common, and probably all of our listeners are familiar with that at some level. Then we move further up the spectrum to what we call precision cleaning, where we're concerned about particle sizes in the range of 1 to 20 microns. These examples could include fuel injectors, valve bodies, medical devices, and those would commonly be cleaned in the range of, say, 60 kilohertz up to 170 kilohertz, with a real center frequency range in the 100 to 132 kilohertz. As we move up to smaller particle sizes, or move down to smaller particle sizes, critical cleaning, submicron particles up to, say, the 1 micron range. Applications such as optics, electronics, disk drive manufacturing, it's very common that the final phase cleaning step in these applications includes exposure to ultrasound in the range of 170 kilohertz up to 350 kilohertz. And then beyond that, we have what we would consider Megasonic critical cleaning, example 7 to 16 millimeter nodes on wafer manufacturing, whereas a lot of applications are now being developed in the 2 nanometer range. Those applications for precision optics and silicon wafers typically employ Megasonics in the range of 500 kilohertz up to 5 megahertz. As we get higher and higher again, those cleaning applications, the cavitation becomes less aggressive, and we actually tend to see cleaning function is actually dominated by something called sweeping, or microstreaming rather. Considerations in frequency selection. Ultrasonic frequency selection, much like chemistry selection, is going to be driven by the characteristics of the soil we want to remove and the substrate materials themselves. The examples of soils could be, again, solid particles or carbonaceous or oxidized materials that are very tenaciously adhered to the surface. Or we could simply be looking at soluble contamination. We also have to consider the substrates and the potential risk of damage there. Yellow metals such as brass, copper, bronze, some of these alloys can actually be very soft, and prolonged exposure to even 40 kilohertz will result in some blemishing of the surface. This is also true with some aluminum alloys and magnesium, and even in some cases, plastic components. Plastics are interesting because in some cases, you actually need to go with lower frequencies to separate particles from the plastics, because the plastic itself tends to absorb a lot of ultrasonic energy. And there's also applications where we need to consider resonance damage, such as printed circuit board assembly and connectors, and frequency regulating devices like crystal oscillators, where the functional frequency of those devices might actually be too close to the resonant frequency of the ultrasound that we're using. So speaking of chemistry selection, it's important to note that chemistries may be specifically formulated for spray and air applications versus immersion ultrasonic applications. Those that are developed for ultrasonic applications are really designed to promote effective cavitation in the solution, perhaps manage foaming and other details like that. Those that are not designed for ultrasonic applications specifically are going to be those off-the-shelf powdered detergents. Those tend to be the high alkaline solutions. We also have a lot of standard multi-use products. You may be very familiar with a green chemistry in a spray bottle that's known to be very biodegradable. We commonly see those used in ultrasonic applications, but they're actually not designed for them. And believe it or not, we even sometimes see folks using dish soap in these applications. Again, it's not that they won't work, but they're not designed specifically for an efficient ultrasonic cleaning process. So let's talk about a couple frequently asked questions on this topic. Often we're asked, can I use just water with ultrasonics to get my parts clean? The answer is absolutely yes in some cases. If you're really looking purely at particle separation it's possible that DI water and ultrasound may be enough to do the cleaning work for you. However, it should be noted that even here, in a lot of cases, it's desirable to have some level of surfactant in the solution, again, to help promote cavitation. Next question, can I use standard off-the-shelf cleaning equipment for my application? A lot of standard 40 kilohertz off-the-shelf units will work for the vast majority of your cleaning requirements. It's important, however, to note that we really want you to look carefully at the risk of damage, the efficiency of your process, and throughput as well. If you think that you're dealing with a more challenging application, it may make sense to consider something with a more tailored frequency selection. What are multi-frequency systems and how can they work to help my cleaning processes? So multi-frequency systems can be developed in one of two ways. One, you can have multi-frequency transducer systems, which are selectable, for example, between 40, 80, or 120 kilohertz. Or you can actually have tanks that have single frequency transducers of different center frequencies mounted on different surfaces. For example, 40 kilohertz on the bottom, 80 kilohertz on the sides, and then maybe even 120 kilohertz on the short sides of a tank. These can all help you tailor a process around the substrates that you're managing and the level of contamination that you're working with. Finally, how do I know if my ultrasonic system is working properly? The most common tool here is the use of a hydrophone, which actually measures, they use a piezoelectric transducer to measure, convert pressure into voltage in the tank. This is a more quantitative approach. There are also systems out there that use pressure sensitive materials or liquid vials that are designed to change color in the presence of cavitation. Those tend to be a more quantitative approach. So with that, should you have any questions, KYZEN works with a number of equipment manufacturers, and we're more than happy to help provide a list of companies that you can engage with to address your ultrasonic cleaning needs directly. With that, I'm going to turn it back over to William. Thank you.
Thanks, Josh. And thank you guys for watching this Tech to Tech session. If you would like to discuss this topic further or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@kyzen.com, and we will have someone follow up with you as soon as possible. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.